Hello, my wonderful Calculus AB students. So we're doing Chapter 2, Section 3, Evaluating Limits. This section is very tedious. Some of you will be frustrated because it is tedious, but you're kind of learning how math works. You can't just assume things. You have to use what you know and the rules that you know to build upon that. Sometimes we assume things and it's not always true, and it gets us into problems. So it's a long video. You probably want to do double speed or maybe 1.5 speed or something like that, but hang in there. So we're doing rules of limits. What can you find a limit of? And as we learn more, this becomes easier. So the first part, the limit of a constant function. So what is a constant function? It always equals the same number no matter where you are. So if you look at this, this function is constantly 3. No matter what you put for x, the y value is 3. Any x, the y value is 3. So they're constantly 3. So if you think about this, the limit as x approaches 1 from the left of f of x, where f of x is 3. So what are we doing here? Where is, not 1 from the left, sorry. We're approaching -1. So that means for this limit to exist, the left-hand side and the right-hand side must be the same. Where is this? I will show you. So let's do gold. There is -1. So we're approaching -1 from both sides. So I'm approaching from this side and approaching from that side, right and the left. Clearly, as I get close to -1 from this side, the y value is always 3. It's constantly 3. So as I approach from the left, the y value is 3. As I approach from the right, the y value is 3. So clearly, this limit will be 3 because the function is always 3. So the function will always be approaching 3 no matter what. Now, just to generalize this, what if you have the function equals c, a constant, where c could be any number? So if c were 2, you'd have that graph. If c were -1, this would be the graph. So as you approach a of a constant c, hopefully you see that the answer will be c. Whatever your constant is, since your function always equals that, it's always going to approach that, whatever your x value is approaching. All right, so this is your first rule. The function's a constant, the limit is that constant. So that's your first known fact. We're giving you that. Okay, what does this function look like? F of x equals x. Hopefully you can see that that is the line y equals x. A slope of 1, a y-intercept of 0. So it's just a line with the slope of 1 through the origin. And whatever x is, y is. So let's look at this limit from both sides of 2. So let me, x is 2 right here. So we're going to be approaching 2 from both sides. As I approach 2 from the left, what does the y value get close to? It's 2. As I approach 2 from the right, what does the y value get close to? 2. So the limit of that clearly is 2. Now we're going to approach -2. Let's do that. -2 is right here. So as I approach -2 from the left, what does the y value get close to? -2. And as I approach -2 from the right, again, I'm approaching this value, x, -2, from each side. And what does the function approach? 2. That's the y value from left and right. Oh, sorry, negative 2. The y value here is negative 2. So that's negative 2. I will put negative 2. And so I think you see a pattern here. When you approach 2, the y value approaches 2. When you approach negative 2, the y value approaches negative 2. Since y equals x, whatever x you're approaching, y is going to approach that also. So go ahead and take a look at example 3. Kind of do that in your head real quick. You can pause if you need to, and I'll give you the answer. So we're approaching 0. Here's 0. And we're going to approach from the left and from the right. As I get close to 0 from both sides, what's the y value from both sides? Hopefully you see it's clearly 0. So here's the general rule. If I take the limit and x is approaching some value a of y equals x, that's going to be a. Whatever that approaches, that's the limit. Negative 2, negative 2, 0, 0. Approaches a, that limits a. Because you're looking for the y value of this, well, the y value is the same as the x. So whatever a approaches or x approaches, that's what the function will approach. So that's going to be your next one. So first rule, limit of a constant is always that constant. The second rule, if you have the function y equals x, the limit of y equals x will just be whatever x is approaching. So in other words, you could think you just plug in x or a for x, and you get a. All right. This is going to be a long video, just warning you. We're looking at all the properties. Technically, these are the only ones that you can use to find limits. And you'll see why this is kind of a pain. All right. The constant one, we already did that. If you have a constant, it always equals k. That will be the limit. The second one is y equals x or f of x equals x. Whatever x approaches, that will be your limit. And again, get comfortable with that in your head. Think of just plugging x in for a or a in for x, and you get a. So that's the other one. So here's the next rule. What if you have the limit, but in the limit you have a constant in front of your function? There's a rule that you now are allowed to use is you can pull that constant out in front and just take the limit of the function itself. So here's your example. What am I going to do? So I don't know how to take the limit of that, but I know how to take the limit of x. There's your function. And I say, gee, I wish that 6 wasn't there. Well, you have a rule that allows you to move the 6 out in front and take the limit of what's left. And if you do that, 6 stays. This limit, by the rule we learned earlier, is just 3. So the answer is 18. All right, so the next property, what if you have two functions being added? How do you find that limit? Again, the only thing you know how to find the limit of is a constant function, the function y equals x or f of x equals x. That's the only ones you know how to do. So what happens when you have adding or subtracting two functions? Well, I'm just going to do one example for both these because you either put a plus or a minus. So I'm going to do this. The limit as x approaches 4, I'm just going to do x plus 3. Now, if it's minus, the only difference is you're going to have a minus in between. So what does the rule say? I have one function, I have a second function. I have an f and a g. I'm allowed to separate into two separate functions. So that's what I'm going to do. This equals the limit as x approaches 4 of your first function plus the limit as x approaches 4 of your second function. Now again, if this was minus, the only difference is you would put a minus there. It's just the sign change. All right, I think we can finish this off. What is this limit? Well, we're going to use that property we just learned. That's going to be 4. And what is this limit? Well, it's a constant. That's always going to be 3. So your answer is going to be 7 for that one. Okay, more properties. What happens if you have two functions that are being multiplied together? How do you find that limit? This says you could take the limit of the first function, take the limit of the second function, and then multiply. So there are two functions being multiplied. The property says I can separate to two separate limits. The limit of the first one, which is x, times the limit of the second one, which is 2x. Again, I don't have a property that has the limit of 2x, but I have the property of just the limit of x. We did that earlier. So I'm going to use a constant rule. I can pull that constant out in front. So that 2 can come in front and take the limit of x. All right, we're almost finished here. So this, we learned this property earlier. The answer to that's just going to be 2. And the limit to this is also going to be 2. So we have 2 times 2 times 2. 2 times 2 times 2, and the answer is going to be 8. So that's that one. Let's just keep going. I know this is kind of tedious, and there's going to be a great shortcut for a lot of these when we get to 2.6. But until we get there, you're kind of learning the process of math. You can only use the properties that you know. You can't make up your own until you're given a theorem or a postulate or something that allows you to. So what do you do for a limit of a function divided by a function? Lo and behold, you're allowed to take the limit of the top function, take the limit of the bottom function, then divide them, as long as the bottom limit is not 0. If the bottom limit is 0, no bueno. Bad things happen. So very quickly, I have a simple quotient. There's a top function, the bottom function. Some may say, can't you just cancel the x's? Yes, you can. But I just want to do this for the sake of realizing there's a property that you can use. I personally would cancel out the x's, but in the future, you're not going to always be able to cancel things out. So this says I could take the limit of the top and take the limit of the bottom separately. And after I do that, then I can combine. Now, I don't know how to take the limit of 2x, but there's a property. If there's a constant, I can move that out in front. So what I'm going to do, I'm going to take that constant 2, and I'm going to move it out in front. So I get 2. This limit clearly is 1. We use that property. The limit of the function y equals x is just whatever your x is approaching. And for the same reasons, the bottom is 1, so the answer to that is 2. All right. We have 3 more of these rules. Let's just keep going. And for the sake of room, I'm going to erase this and use this space down below. Okay, what is this saying? If I'm taking a derivative of a limit of a function and is raised to a power, I could just take the limit of the inside first, then raise it to that power. That's your next property. So here's my exponent. Well, I can take the limit of the bottom function and then raise it to the third power. I'm going to do that. It's going to be the limit as x approaches 2 of x. Then you cube that. So you take the limit of the inside function. Well, the inside function is just x. And as we've done a million times, the limit of the inside is 2. And we leave it cubed, so the answer to that is 8. And this is very similar. Instead of a integer exponent, now I have a fractional exponent, which is just a root. Okay? So a square root is a 1/2 power. So basically we're doing roots here. This says if I have a function and you're taking the root of it, I can take the limit of the inside function first, then take the root. So I can take the limit of the inside function. What's the inside function? It's x. Then take the square root. So I take the limit of the inside function, then square root it. What's the limit of x as x approaches 4? We learned if it's y equals x, the limit is just what the function is approaching. And so that'll get us an answer of 2. And this last one, eventually you're going to learn why. But if you have a polynomial and you want the limit, all you do is plug in a for all the x's. And that's the limit of a polynomial. We will avoid using that because I want you to apply these properties and understand it. You don't understand why that's true just as of yet, but that will be true. I'll allow you to use this on problems where there's multiple parts and this is one of the inside parts and it makes life easier. So we have 4 examples here. If you want, after I do the first one, maybe you can pause and try the other ones on your own. But here we go. It's good practice for you. All I know how to take the limit of is a constant, y equals x. Those are the only limits I really know. So I have to use these properties on these problems. So this is not a constant. This is not just an x, but I see 2 things being added. So I'm going to split this into 2 separate limits. Okay, so again, I know how to take the limit of a constant, but 2x, I don't have a rule for that. But I was told if I have a constant, I can pull that out in front. So I'm going to move this constant out in front, and basically I'm using this constant rule. I can pull the this constant rule. If I have a constant, I can pull it out front. All I did is pull that constant out front. Then we're almost home free. This limit is just going to be 2. And this is a constant. That limit is just going to be 3. So we get an answer of 7. All right, let's just keep going. You can pause and try these. Again, we have things being added or subtracted. And so I can split this up into 3 separate limits. Now, the first limit is x squared. The second limit is going to be 4x. And the third limit is just going to be 3. Okay, I know how to find that. That's just a constant. I don't know how to find that because I don't have a rule for 4x. I only have a rule for 4, but I hope you're seeing the picture. I can move the constant 4 in front. So I'll have a 4 in front. And then what do I do with a squared? I don't know how to take the limit of something squared, but that's where this property comes in. You can take the limit of the inside first, then square it. So I know this is tedious, but I'm going to take the limit of the inside function, which is x. Then I'm going to square that. And the limit of this is 1. And the limit of 3 is 3. The limit on the inside here is going to be 1. And so I'm going to get 1 minus 4 plus 3. It's going to give me 0. All right, let's keep going. I have a square root. What do? That's this root property. If I have a root, I can take the limit of the inside first, then take the root. So that's what I'm going to do. I can take the limit of the inside first, and then take the square root after. That's the property I'm allowed to use. Now, technically, this should be broken up into 2 separate, and then pull the constant out, and then use the power rule. But this is a polynomial, so in this case, I'm just going to use the polynomial rule, which says the limit of a polynomial. All I do is plug in a for x. So I'm going to do that. I'm just going to replace all the x's with my -2. That's going to get me 8 plus 8, which is square root of 16, which is 4. I told you this was going to be long. Okay, next one. The limit as x approaches 4. What do you notice here? I have a division. So this is going to be the quotient rule. I can take the limit of the top divided by the limit of the bottom. So I'll start with that, see where that takes us. The limit of the top is going to be separate from the limit at the bottom. And here's the bottom one. Okay, I'm going to take a couple of shortcuts. This is to save you time because this is a really long video. There's a squared. The rule is I can take the limit of the function first, then square it after. So I will do that. So take that limit, then square it. And I'll talk about the bottom in a second here. Okay, here's the problem. Well, this is a polynomial. The rule is I could just plug in 0 for the x. So I'm just going to take a shortcut. And that limit on the inside is going to be 3. I'm just using the polynomial rule where you can plug the 0 in. So I'm going to let you do that on these multiple, like long problems with pieces inside of pieces. But if you just have a straight polynomial, I don't want you to use the polynomial rule. So once you get the practice and understand the process of math, you have to use properties that you know. You can't make up your own properties. Okay, we're almost done here with this problem. Now, how do you find the limit of a cosine? So I'm going to cheat a little bit. You don't know how to do that yet, technically, because the only thing you know how to take the limit of is a constant and y equals x. So what do you do when you have a cosine? Well, in section 6, you're going to learn if a function's continuous, to find the limit, all you do is plug in the number. So I'm just going to take that rule and just plug in 0. I get 9. Cosine of 0 is 1. Hopefully you all know that. And the answer to this is 9. All right, we're getting somewhere. Excuse me. We're almost done. Piecewise functions are very, very, very important. You have to know how to do piecewise functions. You're going to have FRQs with piecewise functions. You're going to have multiple choice questions. If you don't understand piecewise functions, you will be sad. So this is a good chance of learning them. So I'm going to graph this function, show you basically what's going on. Is a piecewise function, you're graphing 3 separate functions. So in a sense, it's this. You're graphing this. You're graphing the second function. And you're graphing the third function. Well, let me do this. The first one I'll do in blue. It's a line with a y-intercept of 5. So at 5, I'm going to put a dot. It goes to that point. The slope is 1/2. So I'm going to plot some points. It's a rise of 1, run of 2, rise of 1, run of 2. And we're going to get something like this. I'll try to draw a line that goes through all those points. Bam, oh, pretty close. Not perfect, but there is this first function. Then I have x squared. I will do this in red. X squared goes through 0, 0, 1, 1, 1, 4, and is symmetrical. So it's negative 1, 1, negative 2, 4, and then 3, 9. There we go. There we go. And you know what? I might be able to get my thing to draw this for me. Ooh, not bad. Not bad at all. Let me see if I can move these points at all. Okay. Move this. Ay, that's going kind of funky, huh? Okay. There we go. That's my parabola. And the last one I will do in green. 1 over x, what does it look like? I will just kind of draw it for you. It's going to be this. Yeah, that's not very pretty. Whoops. Whoops, 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 whoops.
Attention, Caitlin Nin, please come to
Whoops.
attendance.
Ignore
Caitlin
the
Nin,
announcements.
please come to
Sorry about
attendance.
that. Okay, so there are my graphs, but here's how you understand piecewise functions. This blue graph only exists from negative infinity up to -2. There should not be an equal sign there. Somebody messed up on that. That's bad. Who messed up? Someone did. Let me get rid of that. You can't equal negative infinity. Infinity is a concept, so that's bad. So I'll fix that. Okay, so negative infinity is way out there. -2 is right here. So your blue graph can only exist in that region. So I'm going to erase everything that's outside that region. So let me get this. This is not part of the blue graph because it only exists up to -2. So anything to the right of -2 should be gone. I'm going to erase that. And then you notice there's no equal sign underneath here. That means this doesn't exist at -2. So what we normally do in that case is we draw an open circle. So the blue function only exists to the left of -2, not at -2, open circle. So x squared, which is the red one, I want it to exist both at -2 and at 1. That's why there's equals there. But anywhere outside of those, I need to get rid of them. So I'm going to get rid of anything to the right of 1. So I'm going to get rid of this. And get rid of everything to the left of 2. I want to get rid of everything left of 2. At -2 and at 1, the function exists at both those. So I am going to color them in. At -2, I want a solid dot there. And at 1, I want a solid dot there. So that's the red graph represents x squared from -2 to 1, including the endpoints. All right, the last one only exists from 1 to infinity. I don't know why that's there. Someone messed up. There should not be an equal sign, first of all. So let's get rid of that. You can't equal infinity. Does not work. Infinity is not a number, not a number. Okay, so I don't want to include 1, but anything to the left of 1 I have to get rid of. So let me erase all the green stuff left of 1. So that gets rid of that, and that gets rid of that. Now what happens to the green one at 1? There's no equal sign, so I should have an open dot. So I'm going to do an open dot. But you'll see there's a red dot there. So in essence, it kind of all flows like this. It doesn't matter that this is hollow because it's filled in by the red dot. All right, so that's the graph. Now I want to find a limit of a piecewise function. How do you do this? The limit as x approaches -4 of the function f of x. So we learned for this limit to exist, the limit from the left and the limit from the right both must be the same. So I'm going to do that. First, I'm going to find the limit as x approaches -4 from the left. And then I'm going to find the limit as x approaches -4 from the right. Well, we're assuming you don't have the graph. We drew that, but assuming we don't have that, all we have is this. How do you do that? Well, I want to approach -4 from the left. Do I want -4? I think I messed up. I want -2 there. Sorry, Charlie. I'm making this video longer than necessary. This should be a 2, not a 4. Too lazy to edit this. So how do I do that? How do I look at the left of negative 2? Well, that means smaller than negative 2. So what function exists smaller than negative 2? Well, here's negative 2. This is a function here. So that top function should be 1/2 x plus 5. And then I want to approach f of x from the right of negative 2. Right of negative 2 is bigger than negative 2. What function exists bigger than negative 2? X is bigger than negative 2 here, so it's going to be x squared. So technically, this should be the limit as x approaches negative 2 from the right of x squared. And using the properties again, we should break that into two separate integrals. That constant should come out. But I'm going to use the polynomial rule. All I do is plug in my x for my polynomial rule. So that's going to get us 4. And then for this one, I don't have a rule for x squared, but I learned I could take the limit of the inside first, which will be negative 2, and then I square it, which will get me 4. Whoopsies. Since the limit from the left and the limit from the right are both 4, that means the limit of this function is 4, and that's how you would do that. That's how you use piecewise functions. If you want, I'm not going to spend the time because this is getting really long. You could test at 1, find the limit at 1, and figuring out which function you should use. But again, assuming you don't have the graph, because oftentimes you won't have a graph on the AP test when you're given this kind of a problem. You have to recognize I'm approaching negative 2 from the left. Which function exists to the left of negative 2? There's negative 2. This is left. I use that function. I'm approaching negative 2 from the right. I want bigger than negative 2. Which function exists bigger than negative 2? Well, this works when x is bigger than negative 2. It's that function. So that's how you decide which ones to use. I know this is long, and there's a whole nother section to get to, and we're going to do that now. This is the last section, very long, but I don't think it's difficult. It's more tedious. Okay, let's talk. Let's look at what happens here. If you were to do this the old-fashioned way, you don't know how to find the limit of that. You'd have to break this into two separate limits. Oh, first of all, there's a fraction. So you have to break it up into a top limit and a bottom limit. Then this you'd have to break into two separate limits and use the power rule for that. But we're going to use the polynomial rule. There's a quotient, right? I'm going to do some bad things here. Limit as x approaches 2 of x squared minus 4. Using the polynomial rule, just plug in 2 for that, you get 0. Right? And then the limit as x approaches 2 of the bottom, it's 2 separate. And again, using the polynomial, that's a polynomial, plug in 2, I get 0. Now, if you were to say this, that's bad. College Board doesn't like it because you made an incorrect statement. Once upon a time, you learned anytime you divide by 0, it's undefined. So this here is undefined. This is not undefined. I will explain what I mean by that. This actually has an answer. So to say this equals 0 over 0 is saying this is undefined, which is not true. When the limit of the top approaches 0 and the limit of the bottom approaches 0, that is called indeterminate. I think of it as I'm not able to determine it. It's an indeterminate form. Anytime you have a limit of 0 over 0 or infinity over infinity, it is known as an indeterminate form. There's other indeterminate forms also, but beware, never say it equals 0 over 0. You're lying and you'll lose points. Okay? So what do you show? You show that the top approaches 0 and the bottom approaches 0. Therefore, it's indeterminate. Right now, you're going to learn 2 techniques to deal with indeterminate form. So excuse me. The problem here is you're dividing by 0. Dividing by 0 is bad. So how do we deal with that? I'm going to show you. You're going to rewrite the top. The top factors to x plus 2, x minus 2. You should know that difference of 2 squares. And you will notice that these cancel out. And in essence, this function is the limit as x approaches 2 of x plus 2, and using the polynomial rule, you get 4. Okay, so that's your answer. It's 4. Now, what's happening pictorially? I don't know if you remember, but when you took pre-calculus, you graphed rational functions. And you learned how to do things like this. You learned if something on top and bottom canceled in a rational function, that produces a whole. Okay? I'll do this logically with you. If you plugged in any number like 3, if you put a 3 there, a 3 there, and a 3 there, right? Well, these will be 1. They're going to cancel out anyways. So the answer is just that. You ignore that part. Let's put in a 6. If I put a 6 in all these, that's going to be 8. That's 4, and that's 4. The 2 4s will cancel. So no matter what values you put here, they will always cancel out. And this will be your answer. Except when x is 2. When x is 2, you're dividing by 0, and what you learn, there's a whole. Hopefully you remember that. In pre-calculus, you learned when something cancels top and bottom in rational function, you produce a whole at that point. And you're going to have to know that for this class. It's called a removable discontinuity in calculus. So if you're to graph it, you would just graph x plus 2. So let me do that for you. My colors are getting all messed up here. Okay. X plus 2 has a y-intercept of 2 and a slope of 1. But at 2, you have a whole. So if you're going to graph that, you would say at 2, there's a whole. And you would draw a hole there. This is the graph of that. Because the 2's canceled, x minus 2's canceled, you have a hole. But what you learn from limits, you don't care what happens at 2, only as you approach 2. So because the 0 over 0, you're getting a non-existent function at 2. At 2, this function doesn't exist. There's a hole there. Yet the function exists everywhere else. That's how you get a limit, okay? And it comes out to be 4. So this is one way of factoring, and canceling is one way to get rid of an indeterminate form. People struggle with this. So hopefully you understand the concept, okay? I'm going to go to example 2, and then we'll do example 3. Again, we're going really long. Hang in there. Let me erase this. And you will notice using properties, if you take the limit of the top, you can split this into 2 separate limits. And then the square root, you take the limit of the inside first. So you would get square root of 4, which is 2, minus 2, which is 0. And on the bottom, 4 minus 4 is 0. It's 0 over 0, which again is indeterminate. Indeterminate. And because of that, do not write 0 over 0. By definition, dividing by 0 does not exist. This does not exist. This does. You are lying. Never do that. That's my warning to you. How do you deal with this situation? Okay. The secret, and this is often done in higher math classes, it's just a little secret, and it's something, kind of a trick. I'm going to multiply by 1 because once upon a time I learned, I think in 3rd grade, anything times 1 is itself. So I can multiply by 1 and it doesn't change anything. Well, I'm going to have a special one. What does my 1 look like? Well, I will show you. Let me set this up. My 1 is going to look like this. Again, anything divided by itself is 1, right? So that equals 1. So this times this is not going to change anything because I'm multiplying by 1. But why did I choose this? Because it is the conjugate of that. When you have a square root and you want to get rid of the square roots, you multiply by the conjugate. 1 minus and 1 plus. You'll see why that's so nice. All right. You multiply the first ones, you get x. I should do this with color coding. So these two multiplied together is going to get you x. All right, I'll do the middle ones. Now you do these two. That's going to get you plus 2 radical x. Then, that's too fat. Let me skinny that up. Then you multiply these two. That's going to get you minus 2 radical x. And then the last one I'm going to do are these two, which is going to get us minus 4. Now, why is that nice? Okay. Because one's a minus 2, one's a plus 2, when you multiply and distribute, these will always cancel and disappear. Okay? And it's nice. You don't have any more radicals. It's called rationalizing. Because whenever you multiply a radical plus a number and a radical minus a number and a radical plus a number, they're always going to get plus and minus. They will disappear. You only end up with the first one squared and the last one squared. And so it always works out nicely. Now the bottom, I'm not going to multiply the bottom out. And I will explain that shortly. Because multiplying the bottom is not going to do anything. It's going to make an ugly polynomial, not even polynomial, ugly function. So you don't want to do that because remember, you want to factor and get things to cancel. You want to get your 0 in the denominator to cancel. My 0 in my denominator is that. That's my 0. I want it to cancel. If I were to multiply this out, I wouldn't be able to get it to cancel because it's in a big blob. So I leave it in factored form, preferably factored form. That and that will cancel, and look how beautiful this is. The top becomes x minus 4. The bottom, you have x minus 4, radical x plus 2, and lo and behold, something beautiful happens. The 0 in the denominator that we had disappears. And again, if I take the limit of the top's just a constant of 1. The limit of a constant is a constant. Now again, this you would split up into 2 separate limits. Then you would take the limit of the inside first, then square root. If you do all of that, you'll get 2 plus 2 and get an answer of 1/4. So that will be the answer to example 2. Now for example 3, go ahead and give it a shot. You can pause. This is the last problem we're doing. I will clear this page and show you how to do the last one correctly. Okay, if you're back from your pause, you're going to multiply by 1. What's your 1 going to look like? So your 1, whoopsies, excusez-moi, it's going to be the conjugate. Again, you want to get rid of the radical. So it's kind of weird. In all your previous math classes, you had to rationalize the denominator. In this class, it doesn't matter. I think they did that so you can practice your working with square roots, but you really don't need to do that. So the conjugate, again, if you understand why the conjugate works, you don't have to memorize what a conjugate is. It just makes sense, and I will explain the sense. Because if this is the same as that and the 2 is the same as that, one's a minus, one's a plus, these two will get you a minus that. These two will get you a plus that. They're going to cancel out. That's why you do that. That's why it makes sense to do that. All right, let me do this. You're going to multiply these two first. That's going to get you x plus 2. The radical's going to cancel. Now, those two and those two are going to cancel out. I'm not even going to write that down. The last one you have left is negative 2 times 2. So that's going to be minus 4. And on the bottom, remember, you do not factor or multiply the bottom out. You want to leave it in factored form because your goal is to get that 0 there to cancel out and disappear. And that's going to happen nicely here because the top is x minus 2. That's x minus 2. Since they're both x minus 2, that cancels that. And you take the limit of the top. The limit of a constant is a constant. Now, technically, you break this into 2 separate limits. Then you take the limit of the inside and you square root it. I'm all going to do that shortcut in my head. That's going to be square root of 4 plus 2, which is 1 over 2 plus 2. And the answer to that is 1/4. Whew. That's a lot of work. So that is the end of this lesson. I'll see you all in class tomorrow.